graphically where we are. Instead of, we're going to do a little bit of math today, but let's just kind of refresh ourselves where we were about doing any math. I've got some nice visual descriptions of our box today. Let's just kind of look at how the box works visually, right? And then we don't have to worry about the equations. It's already covered for us. Right, so what I have here, I'll try to remember to post links to this. I have two of these to show you today. Post links to this on my Discord campus. I could put it on Discord. For you to play around with if you're interested. I think it's a cool way to look at this problem. So here we have a particle in a box. Well, what we have is a box and we're solving a wave inside of that box. Right, so this is not an infinite box. In fact, right, this is our potential here. Here we have our potential energy. And our potential energy, I'm just kind of approximating like a box. All right, so it's got a top. Right, it's got a top to it. So there's going to be eventually we can put enough energy in this system that it may escape. So we'll have to look at that in just a second, but we should think that, well, if the particle is low enough energy and it's deep in that box, then it kind of looks infinite to it, right? And so let's just kind of look at that approximation today on this picture and just kind of see how our wave function probabilities, these are the psi squares down here, right? So these are our probability density of position. So this tells me exactly for this energy level, which is the ground state, psi 1, where exactly on average the electron is going to be. Okay, so we get this nice little distribution right here. And it just says on average it's in the middle and it samples to the left and right equally, just like we thought. Right? And this kind of looks like a half, in some ways it kind of looks like a half period of a wave, just like we expected. All right, so nothing too exciting there, right? It's exactly what we showed. And we can just keep moving up. I'm echoing somewhere. That should fix it. Let's just move up levels, right? So as I go to y psi 2, right? Remember that's a sine wave of a whole period in the box. So there's going to be two peaks in a square. One's a negative and one's positive, whichever way you want to think about it. And so when you square, you're going to get two positive peaks, right? And so there's what we call a node. I'll make that comment in a second. But there's this, right? There's a unique spot now in the middle of the box where there's no probability at all. So now this particle, again, it still samples the left side of the box equally to the right side of the box. So this is cut right down the middle. It's the same on both sides. Nothing's changed. But because of the wave-like structure of the particle in this box, we instead now predict that there's going to be a region in the box where we don't, in this energy level, the second energy level of the particle, that doesn't appear in the middle. It only appears on the edges. And that's just a product of this wavelength. Right? And as we continue to go up, right, we're going to increase the frequency of our sine wave, which means it oscillates faster and faster. And that means we're just going to see more and more of these peaks and nodes. Right? We see 3 peaks and 2 nodes here, right? So now there are 2 unique points in the box where you'll not find the particle. And then there will be 3 peaks, 3 kind of average regions where the particle is sampled equally, right? It's going to be here, here, or here, kind of 33% of the time. And I just keep going, right? Just keep going up and up and up in energy, right? And again, we're just adding more and more peaks and troughs to our wave. So now here I'm in the 6th energy level. 1, 2, 3, 4, 5, 6 maxima. And 1, 2, 3, 4, 5 nodes in the middle, right? So we're just getting this kind of harmonic structure to the wave function, right? Every energy level, the frequency of the wave effectively doubles, and we get a faster and faster oscillating wave, which means that again it has this wave-like structure. But notice what's happening as I increase the energy. The peaks, if you will, the distribution is starting to spread. And we just look at that, right? Compare this one where the particle is on average compared to here in the ground state, which you can't really see that on the screen, right? So there's psi 1, right? And it's just kind of localized, very set, kind of on average in the middle of the box, right? It can be on the left and the right side, but it kind of decays pretty quickly. So it's really not near the edges. But as I start to get closer to the top, right, it starts to spend more time on the edges. So the box is now sampling, sorry, the particle is now sampling more of the box on average. Okay, it's still on average in the middle, because it could be over here as much as it is over here. It's still symmetric. But on average, the particle is starting to explore the edges of the box more. Okay, and this is what we look at in the problem set. Right? What you'll see in the problem set is that what we want to do is measure the average position, which we did last class, which for the box is 0. But if you take the square of the position, which is like the variance of the statistic or the standard deviation, right, that measures the width of your distribution, the width of your bell curve, if you will. Here, the bell curve is just the sine wave, the sine squared. But the width is getting wider, right? So that means that on average, you have some distribution of positions. And as the energy increases, that distribution is getting wider and wider and wider. And you can imagine if I extrapolate this to a really high number, and I'll do that by increasing the width of the box, where the energies are proportional to 1 over L squared. So as that makes the box wider, the energy level spacing gets smaller. There's more states per unit energy. Right, watch this. Right, more and more states start to appear inside the box. Right? And all the states start to get compressed in energy too, right? Because it goes as 1 over L squared. And so here's my, again, 6th state again. Okay, it's spread out a little bit because now the box is wider, but it's maybe even more clear now that it sits on the edges more than it does in the ground state, right? Because the ground state here, this is the 2nd excited state. Just kind of compare it, right? You can see here, if you look really closely at this yellow one, right? In the 7th state, it spends a lot more time on the edges of the box, the maximum there near the edge of the box, than it does inside 2, right? So that as the particle increases in energy, it's, again, on average in the middle of the box, but it's starting to sample everything more uniformly. Right? And again, I can go to the top level here. Right? And at this point, right, if you just close, it looks like a tooth, but or a saw blade or a razor blade, or not a razor blade. What do you call it? Like a cut your hair. What's that called? The blades on a razor to cut your hair. And you can see that now the particle kind of just solely exists kind of everywhere. Right? There's still nodes in the middle, right? There's like ridges. Well, there's going to be places where you see the particle, you know, high intensity in these regions. If you have like a detector matrix here, the detectors are bright depending on how many times you see the particle, right? You're going to see these bright ridges, and then you're going to see these dim ones in the middle. But there's going to be more and more of those bright regions, and they're spreading further and further out through the box. Okay, so you can imagine if I take this to infinity, if I have a huge box, let's just do it as best I can on this in this program. And I go up to the top level, right? This is side 39 for this box, right? If you really blur your eyes, what does this look like? Well, it kind of just looks like a flat top. Right? If you can make these gaps between the peaks really, really small, and you have tons and tons of peaks, right? It kind of looks like a comb. That's the word I'm looking for, a comb. It's like a comb. And if you blur your eyes enough, the comb kind of just looks like a flat top. Right? If your resolution is, your eyes are blurry enough that you can't tell, you can't distinguish these edges, the gaps in between each of the ridges, then it just kind of looks like one uniform distribution. Right? So at high energy, right, the particle starts to explore the box uniformly. It can be anywhere with roughly equal probability. Right? There's just as much probability that it's in this quadrant as it is in this one or this one. Right? So it starts to lose that wave-like behavior. Right? It's starting to measure the box uniformly. Right? So just take that, right? This is what I do in the homework. Take that to the extreme, logical extreme, where say you're in the 10 billionth level. Right? If you're in the 10 billionth level of this particle in a box, you've got 10 billion peaks and 10 billion minus 1 nodes, and the gaps between each of the peaks is basically infinitesimally small. Right? So it just looks like a comb that's just continuous. Right? It's just every peaks as far as you can see, and you can just basically think that's just flat. And what that means is that at these high energy levels, the particle basically samples every point in the box equally. There's no bias towards the edges or the center of the probability distribution. It's everywhere. And that's an ideal gas. An ideal gas is just a particle that, or a set of particles that sit inside a box that randomly explore the entire box and fill it equally, right? Equal density everywhere. And so what you get basically naturally out of the particle in the box limit is that when you take it to very large energies, very high energy levels, that effectively the probability distribution looks like an ideal gas. It's just flat. It's an equal probability of finding a particle anywhere in a box. No bias into that. Right. So what happens is that from the particle in the box approximation, if you take that to if you then assume that this box has a mole of particles in it, and you look at average energy of these particles at a given temperature, you recover directly from the particle in the box theory, the ideal gas law. The ideal gas law is just there's a mole of particles in a box that don't interact, that sample the box equally, which is a particle at very, very high energy level. All right, so the homework has you explore that idea. Any questions about this? Okay. Yeah, go ahead.
Because like when you think probability density, it's saying like probability of peaks.
Yeah, exactly. All psi squared is, imagine again that your box is just a series of little detectors that sit at each point, and you count over the course of a long period of time how many each of those detectors, how often or how many clicks each of those detectors get over a period of time. And this is the result you're going to get. Right, so this is position of the detector, and this is the number of clicks. Okay, so this tells you exactly over the course of a million measurements, statistically, where you're going to find your particle, and the exact probability of finding it. And when we talk about bonds, this can be very important, because we'll see there's going to be some ambiguity about what a bond is because of this distribution, this wave-like property. There's another thing I want to point out, and it's quite subtle. So the box is actually at 3 and -3 here. And if you notice, we're looking at this top energy level. This box is finite energy, right? So there's, if my particle has any more energy than this, it escapes, which is why there's no more levels above this one. Right? So it's a free particle at that point, right? So there's like an escape probability. And what do you notice about here, right? So remember that in the particle in the box, let's just go to the ground state, or one of the lower levels, right? That the wave function should go to 0 at the edges. Right, so if we look at this low level here, right here, the level, the box is kind of right here on this edge at 3 and plus or -3. Right, it basically goes to 0 at the edges. Right, exactly like we would expect. Right, I'll go to another one here. Right. You can see that, right? It rolls off, and basically there's no probability of finding a particle at the edges, past the box. Okay, that's great. So it's trapped inside the box, right? That's my interpretation here. There's no probability outside the edges of the walls. It's really trapped. Right, but if I go to the top level, what did we notice? Well, there's a exponentially decaying curve on the edge. So right here at the right, it's almost as if the wave function peaks at the wall and then rolls off at the edge. So how do we interpret this? Well, what this is telling me is that occasionally I'm going to hit a measurement where I found in this level, when the particle has this energy right near the top of the box, that there's going to be a probability I'm going to find the particle outside the box. Right? It's a small probability, right? Because how would we calculate? Right? We would do an integral. So let's think about that for a second. So this is a particle that's barely in a box, if you will. So we have this potential energy that looks like this. Here's our potential. This is X and this is E energy. Right, and I want to look at a particle right here at the edge. Right there. All right, so we'll call that psi n of X. All right, and we'll say that the energy, when we calculate the energy of psi n of X, we get En of X, which is this level En, psi n. And if we go to the next one, this is a free particle. So here we find that the energy is a function of n, where n is a real number. So above the box, there is basically a bulk of states. They're continuous, right? And they're free particle states. They're the h bar squared, k squared over 2m free particle. All right, so so we have what we have down here in the box. We have our bound states, the ones that are trapped in the box, and then directly above it, we've escaped the box, and now we're at free particle. Right? This is kind of like an ionization, right? Imagine this box is a hydrogen atom, and we have an electron that we're looking at, and we're constantly taking that electron more and more energy. It's getting to higher and higher orbits of the hydrogen atom, and eventually put enough energy that it just leaves, and it becomes a free electron. Right, so this will look a lot like, in some ways, a lot like a hydrogen atom ionized. Right? So we have this final bound state of a hydrogen atom with an electron, what's called a Rydberg state. I'll introduce that when we talk about hydrogen. And then eventually you just put a little bit more energy in and it just leaves. And it becomes a free particle. All right, so let's look at the wave function of that final state. And again, I want to look at psi squared because that's the probability. Psi squared of x. Right? That's going to tell me where I'm going to find my particle. And what do we see? Well, I'll put my box here. So this is my box, L and 0. I'll just mark it so we know exactly where it is. And right, let's go back really quickly to the picture again. Inside of the box is just a sine wave, a very high frequency sine wave, right? Which is what we would expect for the particle in the box. It's just a high frequency sine wave. So again, I'll just draw it like this. Let me get rid of this end part here. So we'll just draw it in the middle right now. Right, it looks kind of like this. It doesn't really matter what it looks like. But the important thing is that what we observe is that at the edge, it comes up, and then there's this decaying peak at the end, like this. All right, let's just go back and look at that one more time. But at the edges, on the last cold tooth, if you will, which is right at the edge of the box, there's now this exponential tail outside of the box. Right, so we have this like e to the minus kx dependence here, or e to the kx rather, dependence that rolls off here, right? And so, right, anything that's in this region here, which I'll mark in purple, right? Right, this is predicting that the particle is now outside the box. It's escaped, right? So this is the free region. The particle is free in these regions. And inside of the box, right, from here, from 0 to L, it's trapped. Okay, so how would we calculate the escape probability? There's some probability that when we observe the particle, it's in the box, and then there's some probability that when we're outside of the box, we may observe it as well. It may escape. So how would we calculate that? Well, let's remember that the integral from -infinity to infinity of our wave function squared dx is 1, right? It's normalized, right? 100% probability, right? This just means that there's a 100% probability of finding the particle anywhere in our space. So we know it's equal to 1, right? So all we have to do is just integrate this regions of escape and compare them to the regions that are bound. The sum of those two groups, if you will, the interior of the box plus the exterior of the box, the integral of those should sum to 1. So what we can instead do is break up this integral into two parts. One, we can do the trapped part, the bound part. Right, so that's the bound part. At the integral of all of this, I'll just kind of roughly color it in yellow. Right, that's the trapped part. And then we add to it the probability that it's in the free region, right? And that's going to be from L to infinity. Psi n star psi n dx, and then one for the other side, right? Which is from negative infinity to minus L, psi n star psi n dx. Right, but it's symmetric. So these two purple integrals are the same. Right, these are the same. Right, so I can just neglect one of them and add a factor of 2. Right? So I'll just kind of do that. So it's just 2 of those, right? And so all the interpretation now is that this right here, right, these two sum together equals 1, right? So this yellow integral here is the probability of being in the box. And this is the probability, the escape probability, if you will. It's going to be a small number, right? Because most of the integral is inside the box, right? It's maybe something like 0.9 and 0.1, for instance, or even smaller than that. Right? So there's a very small probability that it will escape, but there's a non-zero probability that it will escape. Right? And what it turns out is that the closer and closer you get to that edge of the box, the higher the probability that you will escape will become. Right? Eventually you get so far above the box energy that you always escape, right? So it smoothly transitions, if you will, as the energy level gets closer and closer to the tip of the box. It smoothly transitions from basically an electron or a particle that's bound in the box to one that's free. Right? And there's some regions that are somewhat in between. You'll have some properties that correspond to, right? You'll have some states that correspond to having a mixture of the two behaviors, where electron may escape from that region, but not always. And so in these regions, like for instance, in this situation right here, right, imagine that this was an electron trapped inside the hydrogen atom. Right? You're right at the ionization threshold, right? You've not pumped in just enough energy to kick that electron out, which is 13.7 volts. Let's say you're at 13.5 volts. And so you're right there at the edge, but not quite. What you'll see is that there will be a flux of electrons coming out, but it'll be a slow rate. Basically, there's some probability that some of the hydrogen atoms in your mixture, the hydrogens will end up on the outside, that will be untrapped, if you will. Right? They'll free themselves. And so even in these states, if you localize your hydrogen atom in a state like this, it will generate a current because some electrons on average, if you think there's some kinetics, if you will, because there's some probability the electron will escape. Right? So even though you're below the ionization threshold, you'll still get ionization, but a very small amount. And as you get closer and closer to that threshold, you get more and more electrons. Right? So the current will slowly increase, but it'll be non-zero even if you're below that threshold because of this little extra at the end. Right? So we call this, I forget the term that chemists use for this, but like pre-ionization, there's a couple different terms for it, right? But there's these concepts where you've generated your hydrogen atom in a state that's effectively bound. But there's some leaky, it's a little leaky. And so you'll get some ionization, but it'll be much slower than you would expect. It's basically not instantaneous, where the electron just flies off, which is what would happen if you pumped over enough energy. But rather, you prepare the hydrogen in some state where it's the wave function of that state is somewhat leaky, and you get a little bit of some kinetics, a little bit of flux of electrons coming out from ionization, right? Even though you're technically below the limit of ionization. Yeah, go ahead.
So like, when you're looking though at low energy levels, like many people,
Yeah.
you have to 100%.
Not at all.
So it's only when you're really at high.
Not at all. Yeah, of course. Yeah, this only, and again, let's just look really quickly at that. And I'll convince you, right? So this is the top level, right? There's a fairly large amplitude component on the outside of the box. And if I go to psi 1, or it doesn't matter, right? These all basically go to 0 at the box at 3. They're basically 0 at this point. I mean, there's always, if the box is finite, there's always a probability that any state in this box will leak out. But as you can see, it's infinitesimally small probability, right? We can calculate it if I had this function, I could integrate it and I could tell you what the probability is that it would escape. Right, but we might learn that the rate of escape, for instance, is on the order of billions and billions and billions of years. Right, so it's basically infinitesimally, it's just not even worth thinking about, right? So we make the assumption that this basically goes to zero and there's no leakage. Right? But when you're near this kind of what we call a proximal state near the top of a potential, right there you have a significant amplitude outside of the box, and that's a measurable rate to measure. A pre-ionization. Does that answer your question?
Yes.
You're welcome. All right, cool. So there's a really beautiful work that's done with these hydrogen states called Rydberg states, where they pump the electrons these really, really high energy levels. All right. So you guys are used to thinking about the 1s and the 2s and the 3s orbitals, right? The n equals like what the height, if I thinking about it, right, the highest quantum number you get to on the periodic table is like n equals 5 or n equals 6. Right? You can take a hydrogen atom or a hydrogen molecule and pump those electrons into the n equals 100 state, the 100s orbital. You're way up there near the top of the ionization potential. The electron is extremely far away from the molecule. It could be multiple bond lengths away from the molecule. Right? And these giant states, and it's just spinning rapidly around the molecule, still bound to it, still orbiting the molecule, still technically a part of the molecule. But you can just sneeze at this thing, and the electron will just fly off. And that's because of this leaking potential right here. If you just impart just a little extra energy, you're going to rapidly blow up this exponentially decaying part of the wave function, the electron just flies off. And you can kind of see this here if I play around with it a little bit. As I bring the height, and maybe it's easier if I make the box a little smaller. So let's look at this top level. So the box now, let me just set it to the box to be at like 1.5. Right, let me go to this top level here. Right, and you see, so the top level is and on this scale well below the barrier. Right? And you can see that the wave function just is decayed by the time it hits the wall. Right, so this state probably wouldn't tunnel that much because the state rolls off before the wall too. Right, but what happens is I start to progressively bring that barrier closer and closer to that energy, that threshold. I have to be very careful because it'll skip a level if I get too close. Right, and what happens? Well, that barrier, right, that roll off here starts to grow exponentially. Well, it's longer, it's the square root of the energy. Slope of this decays. The decay rate goes as the square root of the energy. And so you can start to see that now there's some non-zero probability outside the box as I get closer and closer to this threshold. And eventually it will just blow up to the point where the state will become unbound and then become a free particle, right? So like right here is a good example. You got to be very careful with it, right? Like that, right? So here I'm right at the threshold. Right? I'm still technically bound inside the box, but there's a very high probability I'm going to fly out of the box because I have just enough energy. It's leaky, basically. This leakage, all right? It just gets bigger and bigger and bigger. And then eventually, once I get above this, my wave function just becomes a flat top distribution, which is what you get for a free particle. A free particle can be anywhere. So this eventually, all of these ridges will disappear, and these will raise up like this, and the whole thing will just become flat with no sinusoidal behavior at all. It'll just be flat top function. Because again, a free particle can be anywhere in the box. There's no preference, just in the box. Right, so there's a term, this leakiness, has a specific term that we use in chemistry and physics. This leakage rate, this escape probability. Right, and we'll return to this when we talk about bonds. It's called tunneling. Quantum particles inside of a potential, they have a sufficient enough energy near the top of that potential. They always have a probability of escaping the potential, called a tunneling probability. And this is something that happens practically, right? Tunneling happens in biochemical reactions. The tunneling of electrons is super important in the electron transfer chain and photosynthesis, a million other places. The place where I find it to be the most interesting practically is in the production of semiconductors. Or rather chips. I think you'd rather think of chips instead. So if you think about your laptop CPU, for instance, your laptop CPU is made up of billions and billions of little transistors, right? And each transistor or combination transistor does some sort of instruction, right? So you have all these billions of transistors so you can run Minecraft and Roblox. And, what are some other fun programs? MATLAB, VMD, Keyboard Pro, Discord, right? So you got to have all these. So a typical CPU nowadays, or even a GPU, has billions and billions of transistors, right? Think of a transistor as just a little box that an electron goes into. Right, and of course they have a problem. So there's two problems that they have to deal with. One is that you want to make your computer more powerful, so you put more transistors on your CPU die. Right, but you don't want to make your CPU blow up because first of all, silicon's expensive. They have to make it on extremely pure silicon. And so you want to also make things smaller, right? We always are trying to make things smaller, so they never want to go bigger. That's what NVIDIA is doing right now. For you guys who are computer nerds, want to buy a 5080, you know that those things are like 6 times the size of a GPU 5 years ago. Because NVIDIA is at a point where in order for things to be powerful, they have to put more chips on it. They can't miniaturize it. But typically it's about miniaturization. And so I'll just show you this, for example. So let's just look at some of these miniaturization schemes. Intel is probably the most famous for it. They have what's called the tick-tock model for their CPUs. And what the tick-tock model is how they fabricate their CPU generations. And so Intel, every time a new generation comes up, Intel has to make new manufacturing processes. Sometimes they have to build an entire new fab, which can cost billions of dollars. This is why it's really expensive and why only a few companies in the world make processors, because it's really expensive to do it at scale. And so the way that Intel has been doing it since the 90s is what's called a tick-tock. So on the tick, they create a new fabrication process. They build a new factory, whole new way to lithograph the CPUs. The way they make a CPU now is they take a piece of silicon and they etch all the transistors and all the conduits for the electrons and stuff like that with a laser, X-ray laser. And so they create this new process, and they do it with what they call the process has a life scale associated with it. So this is what is this? I don't remember which one this is. This is Pentium 4. So 1995, 2000 era was the tick for this, and it's 65 nanometers. What that means is that the average distance between two elements on the die is about 65 nanometers apart. Okay? So if you have a transistor here, the next nearest one on average is 65 nanometers away. And then they go to TOC, which is where they build a new architecture with that fab, where basically they build the process, the manufacturing hub, and then they design a new basically layout architecture for the chip on the TOC. Right, so it's about every 2 to 3 years they tick-tock. And it's sped up over the years, right? So now it's on average every year is a tick, or TOC. So every 2 years, Intel releases a new CPU generation that requires a new fabric, a new manufacturing plant, and then a new microarchitecture. And as you can see, as they've improved over the years, the size scale, where are we right now? So I think we're on, yeah, so we're here. This is 20A. This is the Arrow Lake. This is a 20 angstrom process, which is 2 nanometers. All right, so in 20 years, we've gone from 60 nanometers to 2 nanometers. Right? Just as a reminder, we're almost at atom-to-atom distance. Right? The average bond length is about 1 to 2 angstroms. Right? So the distance between two components on the new Intel chip are no more than about 10 hydrogen bond lengths apart, 10 or 15. Really, really small. All right, but here's the problem. What is nothing, right? So what you have on this chip, I'll just draw it on here. What you have on this chip are a series of effectively tubes, conduits that allows charge to flow between transistors. All right, so here's my chip. Right, and I got some transistors here that have some little tubes running between them where the electrons are flowing between them. Right, let's just do it like a square here. Right, so these are my transistors. They're all interconnected maybe. And I have these little tubes flowing between them. What that 2 nanometer says is that the distance between two of these is only 2 nanometers. Right, so the distance, effectively what that means is that actually what it means is that the distance here The distance here, this is 2 nanometers. This is 2 nanometers, and this is probably somewhere less than 10. All right, so you have these effectively these conduits of silicon where the electrons are allowed to flow between the transistors. Well, what does that look like in terms of potential energy? You have electrons being flown through these trapped lines, if you will. Think of these as little one-dimensional particles in a box, or you have an electron flowing through this tube. So what does that look like? Well, if we kind of cut our picture down the middle, so like if I take a slice along this axis right here, and I plot it in terms of x, and then in terms of energy, potential energy of storing the electrons, I basically have two little boxes, one for each of my conduits. So this is conduit 1, and this is conduit 2. All right, and I got some electron moving through here at some energy. All right, so here's my electrons moving through here, and here's my electron moving through here. Right, this is E1, and this is another electron. Okay. Well, I'm going to keep bringing these closer and closer and closer together. Right, as I start to shrink, I'm going to have 2 electron conduits that are effectively right next to each other, like this. Right? And so if I draw my wave functions, right, and if these are sufficiently, these are very, very narrow, thin channels, right? They can only trap electrons so effectively. And so what you'll find is that when you start to draw these wave functions with these 2 states, right, these 2 potentials where an electron is allowed to exist, what you find is that the electron will begin to share its wave function with the other one. Right? There's going to be some interconnection between the two, right? There's going to be some probability that this electron can end up over here, and some probability this electron can end up over here.
I have a question.
Yeah, go ahead.
You say shrink.
Shrink the distance between the two as we make the die smaller. Right. So as these distances get closer every time we make a smaller chip.
Oh, so you're saying why you can't make it smaller?
Right. So the problem is that when they're sufficiently far apart, if you have one electron, right? So let's just say this conduit is assigned to your Minecraft server. And this one's assigned to Spotify. Right, and it's a part of some instruction that's running these, right? But when you start to bring them together, the electrons now have some probability density in the middle. They can share probability between each other. And so there's some probability that those electrons will get swapped. Right, so you'll have this electron moving here, and this one being moving here, and the probability of swap, which is the area under the curve in between, I'll just say in between, so squared, x is not equal to 0. And so there's some probability that, let's say you send this Minecraft instruction here, and then somehow the electron that's associated with that current that's for that instruction ends up on the Spotify conduit instead. Right? And so whatever transistors at the end of conduit 2 gets triggered, which does something completely different than what you originally told the CPU to do. Right, so this is the continuing problem with CPUs, is that as you get smaller and smaller, electrons start to leak across the conduits, across the transistors, because of this tunnel. So we have tunneling across transistors and current conduits in microscopic chips. Right, so ultimately, right, we're already at the point in the last 5 or 10 years or so, we're already at the point where they can't make really any that much smaller. Right, what Intel has been doing instead is making their processors faster, putting more CPUs on a single die, so multi-independently in operating processors on a single die. which requires more power, more heat. Right, so instead of making each processor more efficient and faster, they're just adding more at a time, right? So that's why you buy a server CPU, you get a chip that's got 64 cores on it. It's 64 little independent CPUs all on one chip. Right, that's because they can't make a super powerful one chip anymore because of this, for various reasons. So it's easier just to split it over 64 smaller chips and have them all interconnect. And so that's why I think they're getting bigger now. Why, for instance, computer parts aren't getting cheaper or smaller anymore because they have to, in order to improve performance now, they can't make things smaller and more efficient. They have just to add more things to the chip. So it gets bigger, it gets fatter, it gets hotter, draws more current, and so on and so forth. Which is why your 5090 now takes like a 5090 GPU takes almost as much power as a washer or dryer, or refrigerator will use. And that's because they just have to cram so much on there to keep them powerful. Because they can't make them any smaller. Okay. I want to show you a different experiment today. So what we've been talking about in our particle in a box are states of constant energy. Right? These are states, each one of these states, let me go back to my simulation. Each one of these states, the only thing we can really say about it is unchanging in time, is the energy. Right? It has this energy, but we don't really know anything about its position, right? It's localized across the entire box. But what I can say is that if I have a state that looks like this, it has a fixed energy. Constant, these are states of constant energy. Right? But again, this isn't really a useful way to think about certain processes in the world, right? Because this is what we call a stationary state, right? This is something that's averaged over time, right? This just says if we take 1,000,000 measurements, this is what we're going to get of the position. 1,000,000 measurements of the position. This is what we're going to get. There are statistics, right? But it doesn't really tell me about how the electron is moving in the box, right? Think about it in time, right? Imagine I have this box and I drop the electron in it with some energy. And I watch it propagate, bounce back and forth in the box, right? This doesn't tell me anything about that. Right? So let's look at it from the perspective of a particle that has some defined position, meaning that I can hold the electron in my fingers and say, hey, it's right here. I'm holding it, and now I'm going to drop it in the box and see what happens. Right? So now what I have is not an electron in my hand here. I don't have an electron of constant energy. I have an electron of defined position. I can tell you it's right into here with high certainty. And so I'm holding it with a defined position, meaning it's localized in my fingers, meaning that it's not the wave function, it's not going to look like this. Because this is an electron that's not localized in my fingers. This is one that's delocalized across the entire space. I'm thinking about something that's just right in my fingers. So let's think about what happens with that. And I think it's best to just see it visually. So I've got another fun simulation here. Let me pause it. So what I'm going to do is I'm going to create our particle in a well. Right? So I've got this. What I'm going to do is set this up just like we had before. All right, so I've got this. So my potential energy, ignore the top two things, the bottom two at the moment. All right, so I've set up my potential, okay? So what I have here is a potential energy. Basically, it's, again, finite. Right? There's some energy I can put in it and escape. But I'm interested in how the particle moves in this box and as a function of time when it's localized at very low energy. Imagine I have a cold electron that I drop in there. How does that propagate through the box compared to one that's hot? That's a time dependent. And so we can't use the same wave functions to think about our electron because, again, we're going to localize that electron at a specific point. All right, so let's just say, for instance, let me put the electron right in the middle of my box. All right, and so what I'm going to say is, hey, I have an electron, I'm holding it. I know it's got some, I can measure basically how close it's somewhere in my fingers here. Okay, so it has some uncertainty to it. I don't know where in my fingers it is. But let's just say I hold it like this, right? Right. So I know my electrons are here. So when I drop it into the box, right? The electron's not delocalized in the box, right? I've measured the position, the size of the electron, and I say, hey, the electron looks like this. It's like this big, right? It has to be somewhere in that space. All right, so when I drop that electron into the box, the wave function of it is not going to look like the energy levels that we expect, because those are ones of undefined position. Those are ones that are delocalized over the entire box. Here I'm taking a localized electron with a specific wave. Right, so we call that a wave packet. Right, so what I have is an electron which is a wave, but I've condensed the wave into a specific region that I know of its size. Right, I've given it some size. I can think of it as an atom, right? An atom has some effective size to it. Call it the van der Waals radius. And so you can kind of think of this as the effective radius of that particle. Right? I know it's this size, I'm going to drop it in. Right? And so I'm going to set it, drop it in the middle of the box. And let's see, have I set the, is there any way to set the energies on here? We can do the energy really quickly. All right, so I'm going to set the total energy of the particle to be basically at the ground state. All right, so the bottom of the box is minus 1 eV. So I'm just going to set it to minus 0.8. All right, so it's got a little bit higher energy than the box. Does it let me do that? Why is that not working? All right, let me just bring it down. Letting me do it like negative. Okay, so I'm going to make the electron relative to my box quite cold. So it's got the average energy of my particle. So think about this. We'll have to think about this a little bit. I have a particle that's got defined size, doesn't have defined energy, but it's got some averaging. Say it has some average energy. And we'll say it's about minus 0.8, right? So it's right at the kind of very low energy. It's right above the bottom of the box in terms of energy. Let's just watch how it evolves in time. All right, so I'm going to turn this, I'm just going to let it go, and we're going to let it evolve in time. So let me reset this, tell you what's on there. So this is the real part of the wave function. I'll turn on the imaginary part as well. Right, remember that waves are complex, so they have two components: a longitudinal real one, which is this red. Right, this is the wave propagating in this direction, oscillation of it. And then there's an imaginary part, which is this way, transverse to us in the imaginary plane. We don't see, but it has both of them, and they both oscillate separately. We have an oscillation this way and an oscillation this way. Okay, so the blue is the transverse, and the red is the longitudinal. And then at the bottom, this is psi squared, right? So what we're measuring is our result of our measurement experiment, our position experiment. We're doing it as a function of time. And so every time point, we're going to update our psi squared to see where the particle is, right? So at t equals 0, it's just localized right in the center, right? We've got a little particle that I've dropped in here that's got this uncertainty from how well I know it. Watch what happens. Right? It starts to bounce. And then notice that it propagates like a wave, right? It bounces, and then the wave kind of splits apart, right? And the thing kind of propagates like a wave against the wall. Right? And the whole system bounces back and forth like this. Right? You can see that this is not a simple wave. Right? There's multiple components of this wave, different frequencies of the wave, and they're oscillating against each other. Right? So in terms of position, the position, if I were to freeze the positional point, like right here, let me just freeze it for just a second. I'll zoom in a little bit. Right? And I'm going to ask, right? Let's say I want to write a function for this. Right? Remember that our particle in a box wave functions are sines and cosines. Is this a sine wave of a single frequency? Yes or no? I heard it quiet. I heard the answer. You're quiet. No, obviously not. It's a composition of many frequencies, right? Right. So this wave function, whatever it is, right? Whatever it is originally is this, right? It seems perfectly reasonable if I have an electron in my hand, that its probability distribution looks like this, right? It's on average in the middle of my hand, between my fingers, but there's some width to it. And then, so this looks like a very simple function, but as a function of time, what we see is actually there are multiple frequency components in here And they oscillate kind of at different phases. And as it starts to bounce off the wall, those sine waves that are composing this wave function, there's many of them, are starting to oscillate out of phase with each other. And so you get this kind of funky sine wave signal. Right? It goes from what looks like a little pulse to something that's got multiple peaks, and it seems like it's got multiple oscillating components adding and subtracting to each other. So what's the interpretation of this? Well, first of all, this thing very clearly propagates like a wave. Right? It looks like a wave bouncing back and forth between two walls, like a wave pool. Right? But it's very clearly multiple frequencies. This is composed of multiple frequencies. Right? So it's not just one sine wave like our energy states. Now remember, our energy wave functions of constant energy is just a single sine wave of a single frequency. But this is composed, right? This particle that has a localized position, meaning I can hold it in my hand, I can tell you how big it is. When I look at its wave function, it's actually defined as a multiple sine waves added together. I don't know what the composition of those sine waves are necessarily. I could figure it out with some tricks. But it's very clear that this is more than just one sine wave. All right, so if each energy level is associated with a wave of a given frequency, then this means that this particle is existing at multiple energies at once. Each energy level has its own assigned frequency. So anything that shows multiple frequencies in its wave means that it's composed of multiple energy levels. So this particle is in a superposition, if you will, of multiple different levels of energy. So some of it could be in the ground state, some of it could be in one of the lower excited states. But in general, it's actually, if you were to represent this particle in terms of its energy levels, it's actually in multiple at the same time. It's oscillating with multiple frequencies. And the only way for that to happen is that if its energy is distributed over multiple states. So when I measure if I ask, as this particle is bouncing back and forth, and I ask the question, what's your energy? Well, it might say it's in the ground state when I first measure it. And then if I measure it again, it might say it's in n equals 2 or n equals 3. Then I measure it again, it might be in n equals 4. Right? And the probabilities of finding which energy it's in every time I measure the energy depends on where it is in the box and its relative kinetic energy. Right? So as I make the particle move faster and faster, more and more energy in the box, the energy levels that it samples or exists in, if you will, are higher and higher in energy. Right? Let's go look at that. Right? This is a very kind of low energy particle. Let's boost up its energy. So instead of it being near the box, let's just put it halfway through the box. All right, let's just put it right in the middle, which is, let's just put like minus 0.10, right? So given a little bit more energy, right, this dashed line here is where the average energy of this particle is. This is how much energy I drop it in with. And again, at initial time, it still looks like the particle that's somewhat localized around my fingers. Now I'll turn it on and let it bounce around. It bounces around with more momentum. And there's more, as you can see, there's more richness. Right? There's higher frequency components interacting in here now. Right? And that's because the particle's at slightly higher energy. So this, if you think about the state, the particle in terms as being a combination of different energy levels, as its average energy increases, the energy levels that it samples also increase, which are higher frequency. I'll just keep cranking it up. Right, what happens if I put it closer to the box, the top of the box? Right, so now my energy is almost near the top of the box. Right, you can see it's moving with more momentum. And then what do we see here? Look, it starts to leak outside of the box. Watch this again, very carefully. Right, you can see it doesn't quite have the same behavior as it did before, in the sense that the particle is no longer really bouncing back and forth against the walls like they were mirrors. At low energy, it was just bouncing back and forth between the walls, right? Like they were just reflecting back and forth. But now that I'm closer to the top of the barrier, some of that probability distribution leaks out. So when that particle hits the first wall, there's a probability it's going to bounce backwards, which are these ridges. But there's also some probability that it will escape. Right, let's watch it again. Watch on the right side of the box after the first oscillation, right? There's this huge amplitude that just leaks out, right? And what that is that electron, basically, if you're, this is the result of many measurements of this trajectory. You're dropping an electron and watching the trajectory go, doing it again, doing it again, doing it again, taking an average. And what you find is that on average, a decent number of those electrons that undergo this trajectory escape out the side of the box. And then they go propagating away. Right? And the amplitude inside the box is a lot smaller than it was before because a lot of that probability has escaped out to the edges. Right? Everything's conserved, right? So as the particles in time leave the box, the probability of finding inside the box decreases as well. Right? And then eventually the leaking habit kind of ceases. It kind of leaks every once in a while. You can see there's a little bit of leakage here, a little bit here. So every bounce or so, it leaks back and forth. But eventually what's remaining is what's stored in the particles that are left inside the box. And as you can see, they oscillate very high frequency. Right? They have many, many frequency components due to the fact that there's lots of ridges here. And again, that's corresponding to the fact that its average energy is in one of the highly excited levels, or sampling the excited levels of a potential. And you can see that even more dramatically if I make the box wider. That lets me. B1, B2. So if I make the box really big, which again puts many more energy levels up near the top, it slows the kinetic energy down because it goes as 1 over L squared. So it's slowing down, you can start to see as it starts to bounce, more and more high frequency components are starting to appear. Like you've got all these ridges, right? And that's because the energy's up here and it's sampling like the n equals 12 or the n equals 15 levels, really high up there. Those are signs that have 15 peaks. And so the oscillations look a lot like those wave functions out up there. The wave functions of constant energy near the top of the barrier, high energy. All right, so this is what's called a wave packet, right? So this is what this is saying is that if I choose to represent my particle, if I hold it in my hand, meaning that it has a defined position, I lose information about its energy. Right? The only type of particle inside my box that has fixed single value of energy is one that's completely delocalized in the box. Right? Those are states of constant energy, or signs. But the moment I take my electron and hold it in my hand and say, hey, it's got this much width, it's this size, then I lose all that information about the energy. The energy information it's been delocalized in energy instead. I have a localized position and now delocalized energy versus the old case, which was delocalized position and localized energy. So we have this relationship, if you will. We have this give and take. If we know something about one of the variables, we don't know much about the other one. This is critical, right? We saw this with color and flavor. Remember, if you define something in terms of color, you don't know anything about its flavor. The moment you measure flavor, you lose its color. Well, it turns out that position and energy, or position, and we'll see position and momentum, have the same property. That if you know one to some limit, you don't know the other one to that limit, and vice versa. All right, so they have a give and take, just like color and flavor. But remember, color and flavor, it's just an on-off switch. If you know one, you don't know the other. When it comes to momentum and position, they can have distribution, right? They're continuous. So you can barely know the position of a particle, or you can really know it, and that will correspond to you not knowing the momentum at all, or knowing it fairly well. All right, so there's kind of a smooth loss of information as you make one better known than the other. Let's explore that for the rest of the class.
I have a question.
Yeah, go ahead.
So, could you explain why the momentum changes? Because I understand leaving the box, why does it go slower versus quicker?
Well, remember that the energy of a particle in the box is its kinetic energy. And so remember that the kinetic energy of the particle goes as 1 over L squared. So all things being equal, constant energy, your kinetic energy, all things being equal, your kinetic energy of the particle is going to get slower as the box gets bigger. So it goes as 1 over L squared.
That makes sense.
Yeah. But I was gonna say the frequencies of the wave function increase because as the box gets bigger, the energy level spacing gets smaller, so there's more energy level in the box for a large box. So that's why it looks like it's propagating more slowly, but it has more oscillations. Because it's a higher frequency, but the box takes longer to move, so it has less kinetic energy. Okay. Just a give and take. So we have this give and take between position and momentum, right? And let me ask you why I say momentum, because we've been talking about energy. Well, let's remember what energy is in this system. So I'm just going to say we have a give and take. Between position and momentum. Now, why momentum? Well, remember what the energy of this particle is. The kinetic energy of the particle in the box, the operator is minus h bar squared over 2m d by dx squared. Second derivative. All this is how we derived it, this is the operator for the square of the momentum divided by 2m. Okay, so when I say that we're creating particles of defined energy, I'm saying that we're creating particles of defined square momentum. Right? Think of the square of the momentum as like the magnitude, right? So it's got no directional component at all. It just tells you something about in some ways, the net kinetic energy of the system, right? It's something about the motion. It doesn't have any direction in it. Right? So when I say that sine n of x, these functions that we derived, 2 over L sine n pi x over L, these are states with defined momentum squared. Right? So there's one value of the square of the momentum. Right? Which means that they're defined with for P for momentum up to direction, because we don't really know which direction it's going, and complex phase. Remember, it's a complex value. Okay, so what this means is that, so remember, momentum is a vector, so we don't know any knowledge about whether it's moving in this direction or this direction. And remember, it's also a phase, so there's an imaginary component associated with it. So we don't know anything about that imaginary component cleaning. But on average, there's a net. Think about it in terms of velocity vector, right? A velocity vector has a speed, the scalar part, right? And what this means is that we know the scalar part of the momentum. Right? So we know roughly what mv is in terms of the scalar, nothing about the direction or the phase. Right? So we know the scalar. Right? Which is equal to classically its mass times its velocity, right? The absolute value of its mass. Okay, so what this means is that when we define a particle of fixed energy for the particle in the box, we're kind of defining roughly how fast it's propagating in the box, right? Some sort of momentum. Right? We saw that with the free particle too. Remember, the energy is proportional to this k, which is just the momentum, how fast it's moving, how aggressive the frequency is, the frequency. So we know this momentum. Right? So when we define a particle with a localized position, right? And I'm just going to use a very simple function. I'm going to use a bell curve for it. Imagine that we have this wave function we'll call of position x, which is a function of x. I'll call it x naught. We'll say it's centered at x naught. Is some component a e to the minus k x minus x naught squared. If I were to plot this function, on x naught, it would look like a bell curve. This is a bell curve. Right, and the width of it delta x, if you will, is on the order of 1 over the square root of k. Okay, so this is the way I'm going to think about a localized particle. I'm going to say, hey, I have it in my hand. It's right here. I know that on average it's sitting, let's say, between my thumb and my index finger, but there's some uncertainty to it. Right, so here's the point between my thumb, and there's some uncertainty it's in there, but I know for certain it's between my fingers. I can feel it. It's constantly shocking me. That's not how electrons work, but you can see it, right? You can think about that, right? I know I have an electron in it because I'm measuring the current between my fingers and I'm constantly feeling shock. So I know there's electrons. And I know it's going to have this distance, right? So the question is, therefore, so if I've localized this particle to a very specific location, what's its energy? Well, this requires a little bit of derivation. I'm just going to give you the result. That's a very, very critical result. So if we have uncertainty in position, delta x, what is delta E? What's our uncertainty in energy? It's a great question, right? When we saw that a particle that has a fixed position or a simulation doesn't seem to have a fixed energy, has many frequencies. And the answer is it lies within the math, and it has a really nice name. This is what's called the Heisenberg uncertainty principle. There's actually different Heisenberg uncertainty principles, but the one that we really care about in here is it says that the uncertainty in the position of your knowledge of the position times the uncertainty of your knowledge of the momentum. Right, so this is error or uncertain position. And this is error uncertain in momentum. Remember, a momentum is somewhat like the square root of the energy times 2 times the mass. Right? Just kind of think that P here is kind of like P squared over 2m. Yeah, so it's kind of like square root of 2m E. The absolute value of it, rather. Momentum is 2m E. This is always greater than or equal to h bar over 2. What this means is the interpretation of this is very straightforward. It says that as you localize the position of your particle, say, I know for certainty it's here in my box, not in the localized across the entire box, where I have no idea where it is. It could be anywhere. I know exactly where it is, or within some certainty, uncertainty delta x. Then that means that my uncertainty in the energy or the momentum is inversely proportional to that. So as delta x gets smaller, meaning I localize my particle closer and closer and closer, the uncertainty of my momentum or my energy increases. All right, so a particle that's perfectly localized that would be something that looks like this in X, where it's 0 everywhere, and then suddenly there's at 1, this is psi squared. Right? It's just a point in space, right? It's 0 everywhere else. Right? Just a point in space. What this means is that if I know exactly where my particle is, I know nothing about its momentum. Completely delocalized, which means it can be moving in any direction, any energy. In fact, if I were to transform this now to a wave function, not in terms of x, but in terms of momentum, right? So if I plot this in terms of momentum and then ask what's the probability of finding a particle at x momentum, at p momentum, this is a sine wave. It's completely delocalized. looks like a sine wave. I'm not going to give you a formula, but it's a sine wave. It's completely delocalized, right? So all momentum are possible up to psi squared. So there's going to be momenta, just like remember when we have a fixed energy, when we put our particle at fixed energy in the box, there are positions or nodes where there's no probability of finding the particle, right? So that nice little the Coulomb structure. So now let's flip the idea. Instead of knowing exactly what the energy is or the momentum, we know exactly the position. Then that means that the momentum function, the probability of finding the particle at a given momentum or energy, is now delocalized. And there are going to be energies that are preferred and energies that have no probability, or momenta that are no probability. So we have localized particle. Delocalized momentum or energy. So there's always this give and take. Right? The opposite of this, of course, is what we've already saw. There's delocalized wave function psi in pi x over L. The same idea. There you have a localized momentum or p squared. P is the point, that's the energy of the particle, and the position of the sine wave. Likewise, your x is a point, your position, your momentum is a sine wave. Right? They're always interconverted like this, right? If you know one, you don't know the other.
Can I ask you a question?
Yeah, go ahead.
So I'm still like slightly confused though on how a sine wave would suggest that it's completely localized, because like, wouldn't that still suggest a certain sort of probable?
Yes.
So why, but how are you like, how,
I don't know what you mean.
like, why do you know it's a sine wave, and how would you know what kind of sine wave it would look like?
Oh, yeah, I didn't want to do this math.
I'll just think that's fine.
So the answer is that the technical answer is that position and momentum are related through what's called a Fourier transform. They're basically what you do is if you have a momentum wave function, or say if you have a position wave function, you can calculate the momentum wave function by taking a Fourier transform with it, which is where you project the wave function onto an infinite series of sine waves and then find the amplitudes. It's like taking a spectrum. It's kind of complicated. Again, it's a very technical answer. And so what you can show is that if you have a wave function of position that is just a single point, it's just called a delta function. It's called the Dirac delta function. If you take a Fourier transform of the Dirac delta function, you get a complex sine wave. So it's just by built into the math.
Then the only other thing is when you say all possible up to psi squared.
Yeah, well, in the sense that there are momenta that you won't see because it still oscillates. Right, so the choices of momentum vary. Right, there's going to be some momenta you see and then some you don't see.
Yeah.
Right, but this continues on for infinity effect. So it could be anything. It could be moving at roughly this. It could be moving at relativistic speeds. There might be some amplitude around that as well, and there might be some nodes where it's not possible.
What is the up to psi squared? That's all.
That just means that it's not. It can't be any momenta. I mean, it can in the sense that this extends to infinity. There's just specific momenta where there's very low probability.
Okay. Thank you.
I mean, up to the probability of the psi, yeah, of the wave function. Right, so the momentum probability oscillates like a sine wave. So there's going to be ones that it shows a lot when you measure it here, 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 and here, and there's going to be ones you'll never see here, 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 and here. But this function extends on forever, completely delocalized. So you have this alternating probability for any value of p. Right, and again, this just comes from the math. So when you take this function, you do a Fourier transform, you get e to the I omega p, or e to the I omega p, which is the sine wave of two components, just like we expect.
Thank you.
Yeah. All right. So again, you may not understand exactly what this is going to, but this has very, very, very critical consequences that we're going to see in the next module. That will tell us, very critical that tells us about how bonds. So this really comes into the case of a bond, because what we're going to find with a bond is that its wave functions at constant energy look a lot like this function, a bell curve. We're gonna have solutions to our wave function that look like bell curves. And so there a bond in some ways is a particle that's confined in a space that has a semi-defined position. It has a semi-defined position, right? There's an average bond line. Right, and that means that if you look at this particle, if you look at this bond in terms of the average bond length, it actually exists in many different vibrational states, so different energy levels. And so this has deep consequences when we talk about bonds. And it's also going to be the proof of why there's this 0 point energy we've talked about, where the particle in the box can't have zero energy, it has to have some amount of energy. And the reason why has to do with this Heisenberg uncertainty concept. We're not quite there yet. We'll get to it soon. All right, so I have one more lecture on the particle in the box. What we're going to do next time is we're going to take the particle in the box, we're going to do spectroscopy. So we'll look at how it interacts with light, and then we'll move on to bonds from there next week. All right, have a good one, guys. What's up?
So I was looking at the homework and I have no idea what I did.
Well, so we had a fun leadership night class.
Like I can figure out
The-
two, but one I don't know what's
All
going
right,
on.
so I don't understand. These look okay to me.
Yeah, that's what I did. It's just slightly different. I realized I didn't have the n value in there. But
Yeah, I did it completely general,
okay.
and you assumed n equals 1 there. Yeah, and it's really easy. Anywhere you get a pi, you get an n. So it's actually 2n squared pi squared down here, and that's the only thing that changes.
Okay.
Every pi is associated with an n. So this is the right answer. It's a little different than what I have,
Yeah,
because I think you've distributed some numbers that I didn't distribute.
I
Mine-
might have.
Mine's like L squared over 6 times something, or I forget exactly.
Yeah, I have what you have.
This is the
gotten
right
for
number.
it. Yeah, that's what you did. I didn't get any numbers when I did it.
What's that?
I didn't get any numbers when I did it.
Oh, okay. No, this looks fine to me.
Thank you.
I was gonna say,